gonna be booking it today. My goal is to get you all the radicals, and honestly, I really want to leave some interesting fun facts for the end, because that's really just some neat applications of radicals, and I feel like class has been very, very content heavy for the past few weeks, so I want to hopefully have a little bit of time to talk about some stuff. So we're talking about radicals. I thought nothing would be better than a dose of the Sex Pistols this morning, and so that's our theme song, it's Anarchy in the UK. What says anarchist more than this face? Right? That's clearly the face of an anarchist. All right, so last time we were talking about radicals. We did a little bit of an introduction. We talked about hetero versus homolytic cleavage, and then we talked about radical stability. So what we found is that it very much goes hand in hand with carbocations, right? So just like a tertiary carbocation is more stable than a primary carbocation, a tertiary radical is also more stable than a primary radical. And so those two things, they are similar, right? So what we want to do is we want to start thinking about the CH bonds that can undergo homolytic cleavage to form these radicals. That's going to be important. And so to form a tertiary radical, what we could do is say have a material with 3 R groups and a hydrogen, or what we could have is say a methyl radical. And so in that case, we have CH, H, H, H. And so this would form a tertiary, and this would form a methyl. And so what we want to think about is what is the effect then on the CH bond strength. Now, all right, so these are going to be very similar in energy, right? These two starting materials, but certainly the structures are not. And so what's more stable, a tertiary or a methyl radical? Definitely tertiary, which means which is going to be a more downhill process, this one or this one? What's lower in energy, tertiary or methyl? It's tertiary, right? So tertiary is sitting way, way down lower in energy. And so what that means is that the reaction on the left is definitely going to be an easier reaction than the reaction on the right. So this is easier reaction to undergo, which means this is a harder reaction to actually take place. And ultimately, we're talking about thermodynamics here. So what do you think the effect of that is on the strength of this CH bond? Do you think it's going to be, when we compare the left one to the right one, do you think it's going to be easier or harder to break this CH bond? It should be easier, right? Because it's going to undergo an easier reaction. It's more thermodynamically favorable to go that way. And so if it's easier to break this CH bond, do you think it's going to be a stronger CH bond or a weaker CH bond than the one on the right? It should be weaker, right? Because we're talking about ease of breaking the bond. If it's going to be a bond that's easier to undergo homolytic cleavage, that's a weaker bond, right? It takes less energy to break that bond. So in fact, what we see for the energies of these bonds is this is going to be about a 381 kilojoule per mole bond, whereas the CH bond on the right is about 435 kilojoules per mole. And that's part of the reason that the methyl radical is so much less stable than the tertiary radical. It's because, well, this is simply a stronger bond. It's harder to undergo homolytic cleavage, and because it's more difficult, we end up with a less stable radical. Those things are tied very tightly together in thermodynamics that we won't get too much into. All right, so when we have a more stable radical, that means we have a less stable CH bond or a weaker CH bond. So that's stability in terms of substitution, right? It's very like carbocations, tertiary, secondary, primary, methyl. What else did we consider when we talked about carbocation stability? Starts with an R. Starts with an RE. Resonance. Yeah, all right. So in resonance, let's think about what the impact could be. So we could have this radical, and then let's say we have this radical, and then we'll just use a tertiary radical over here. So we'll just say RC, R, radical here. All right, and so knowing what we know about carbocation stability, of these 3 radicals, which do you think is the most stable? Well, we want to think if basically we can delocalize the radical. Radicals are relatively high in energy. They are electron efficient, not as much as carbocations. And so we want to think if we can stabilize these things via resonance. And so what we can do is we can try to draw some resonance structures for this radical. Now, do we use full arrows? Now, what do we use? We use fish hooks, and so when we do our fish hook mechanism, we'll draw a fish hook here, and so that's indicating the movement of 1 electron. So then we'll break this pi bond, will undergo homolytic cleavage such that only one electron is going that direction, and that means that we've freed up another electron to go this direction. So what we end up with will be a structure that looks like this. And so do we have a resonance stabilized radical in this case? Yes, we do. And so furthermore, is this the only resonance structure that we can draw for this radical? It is not, right? There's going to be two other structures. We can keep moving this thing around the ring. And so I'll let you draw these out on your own. We'll say that there are two more structures that are possible. All right, so then in the middle radical, what we've got is, again, this is going to be a special case. And in this case, what we've got is going to be a radical next to an alkene. And this gets a special name. This gets referred to as an allylic radical. And so an allylic radical is stable for the same reasons that we've seen over here. And so, again, we can draw a resonance structure with our fish hooks. It can move that radical around. And so what we see is that in this case, there are two possibilities. And so this is going to be a resonance stabilized radical. Is there any resonance possible here? No. I mean, there's no pi bonds, right? So what we see is we're going to have a stability coming in from the resonance that can result from pi bonds and radicals. And so ultimately, whenever we have resonance, just like with carbocations, those resonance stabilized radicals are going to be more stable than non-resonance stabilized. So these will be more stable, and these will be less stable. Why is the one with benzene more stable than the allylic radical? Yeah, there's more resonance, right? We can spread that radical off around over onto more carbons. And so just like with a positive charge, if we can spread it out more, it's more stable. Same thing with radicals. And so really it's just the same idea here. All right, so let's see how that affects CH bond strength. So let's think about which CH bonds we would have to break to form these radicals. So for our benzene example, it would be one of these CH bonds. For our allylic radical example, it would be one of these CH bonds, and then I guess we would have a structure here that looks like that. So we've already talked about actually the strength of the CH bond in this structure on the right. So if we go back up, we see it was about 381 kilojoules per mole. And so knowing what we've talked about, we just talked about how the stability of the radical can really impact, or it might impact it, or might be a result. It's kind of a gray area. They blend together. It's thermodynamics. So as a result, this CH bond is 381. Do you think this CH bond is going to be stronger or weaker? Weaker, right? Because it's going to form a more stable radical. The more stable radical we have, the weaker our CH bond is as a result. And so what we find is that the CH bond for an allylic radical is around 364 kilojoules per mole. Finally, we have our most stable radical that we've talked about, and we find that the CH bond here is about 356 kilojoules per mole. And so when we talk about radical reactions, we're going to learn about three of them today. What we're going to find is they have regioselectivity, and that regioselectivity is going to be determined on the strength of all the CH bonds. Basically, we're going to look for the weakest CH bond. That's going to be the easiest one to break and form a radical, and that's where we're going to do our reaction, just like that. All right. So for example, you might see something down the road that looks like this. So let's say we want to locate the weakest CH bond. And I have had no food and lots of caffeine. All right. So let's say we have a structure like this. And so there's a lot of CH bonds in this, obviously, but it's up to you to figure out what's going to be the strongest CH, or the weakest CH bond. And so let's see, starting from left to right, we have a couple of primary carbons. Those are going to have pretty strong CH bonds, so we don't worry about it. Here we have a tertiary, and so we've seen tertiary carbons have relatively weak CH bonds. What about here? Do we have a CH bond here? No, and so even though it's more substituted, because now it's a quaternary carbon, there's no CH bond to break, and so we clearly can't form a radical here. If we did have a quaternary radical, we would have 9 electrons. Is there a problem with 9 electrons around carbon? pretty big problem, right? That breaks the octet rule. So no quaternary carbons, whatever you do. So then we keep moving right, and so what we find is here we're going to have a secondary CH bond, which we can consider. And then we see we have a pi bond, right? And so whenever we have an sp2 CH bond, we're going to say that they are relatively pretty strong. And so what that means is that when we see this hydrogen and this hydrogen and this hydrogen, these we don't really need to consider. Those are pretty rock solid, and we're not going to end up with a lot of sp2 hybridized carbons with forming a radical. So we don't worry about it. So really it comes down to the tertiary versus the secondary. And so who thinks, or what do you guys think? Is it going to be the tertiary or the secondary? Tertiary is more substituted, right? But the secondary has a special key aspect to it. What's it next to? It's next to a pi bond, right? And so even though the tertiary has more substitution and we would expect it to be more stable, we see that the secondary is right next to that pi bond. And so what that means is that the secondary is actually an allylic CH bond. And so what did we see above? What's going to be more stable? It's going to be a tertiary radical or an allylic radical? Definitely allylic, right? And it's because of that resonance stabilization. And so ultimately what we find is that the weakest CH bond is going to be on that carbon right there. So it's going to be important that you be able to look at relatively complex alkanes, to consider all the different CH bonds that are involved, and then pick out the one that's going to be the weakest, because ultimately that's where our reaction is going to take place. All right, so let's jump right into reactions. This will be Roman numeral number 2. So we're going to call this the radical halogenation of alkanes. And so ultimately what we see, so when we talk about alkanes before, we said they're not very reactive. Granted, you can set them ablaze and we could use the heat. And in that sense, they are pretty reactive. But they don't do a lot of interesting organic transformations because basically they end up as soot and CO2, and that's not very useful in organic chemistry. So here's where that changes a little bit. So we can take a molecule like methane. We can react it with chlorine gas, so Cl2. So we're probably going to try to dissolve our gas into a solvent and then feed it in. So we've got chlorine that's reacting here. And so when we try this reaction, nothing happens. It just stays as methane. And so that's because we've left out one key aspect of this. We've left out this stuff. All right, what is this stuff? Well, that is an H, and that is a nu, the Greek letter nu. And so this is special chemist shorthand for light. And so in most cases, we're going to use light in the ultraviolet region. So what you'll literally do is you'll take your reaction, you'll put your methane in it, you'll put your chlorine gas in it, and then you'll take an ultraviolet lamp, set it right next to your flask, and just irradiate it with UV light, because nothing will happen unless we give this thing light. Why is that? It's honestly a little beyond the scope of this class, but if you're doing a chemistry major or minor, you'll find out the reasons going forward. So we'll just leave it at that. We want to make sure that we include light whenever we're doing the radical halogenation of alkanes. All right, so mechanistically, what's going on? When we talk about the mechanism of radical reactions, they're not really, they have a little different format than the typical reaction mechanisms we've seen before. And so in all of these cases, what we're going to see is that we have three-step mechanisms. So those are referred to as radical chain mechanisms, and we'll see why that is in just a second. All right, so the first step of our radical mechanism is what we refer to as an initiation step. So the initiation word it's referring to radicals, right? So it's going to be the initiation of radicals. If we're going to do this reaction, we have to generate some radicals somewhere, and this is pretty much where that happens. All right, so we're going to undergo the initiation of radicals, and this doesn't have to happen a lot, because what we're going to find is the next step doesn't really use up the radicals, it regenerates radicals. So we'll see that in a second. So not a lot of this has to happen, but a little has to happen so that we can initially generate some radicals. So what happens is we have actually our chlorine And so we don't start with our organic stuff here. We're going to start with our chlorine. And so our chlorine is hit by a light. And so essentially what is going to occur is going to be a homolytic cleavage of these chlorines. So what we end up with is 2 Cl radicals, just like that. And so that's our initiation step. That's how we actually generate our radicals at the beginning of the reaction. All right, so step number 2 is going to be propagation is either with an O or an A. I feel like an A. Yeah. Okay. All right. So propagation. And so propagation is the important step. Propagation is where the action is. Was there a concert or something last night? Yeah. I've overheard some people talk about it. I was just curious. Okay. The chain smokers, right? Yeah. That's how I know I'm old, is I don't know who that is. Don't groan about it. All right. So the propagation step, that's where our you'll be 31 day. All right, so 31. The methane comes in, and so now we're going to actually include our organic stuff, and we're going to see some things happening. So what will happen, this is actually a little 2-stepper propagation step. We're going to start with methane, and of course we've generated chlorine radicals. And so what we're going to do is this chlorine radical is going to come in and it's going to abstract the proton. And so what does that mean? So again, we're going to use fishhook mechanisms. We're going to use our radical electron to form a new bond between the chlorine and the hydrogen. And so one of the electrons gets used up here in this bond. So what's going to happen to this other electron? It's going to scoot right back over to the carbon, right? So in effect, what we're going to do is we're going to generate a methyl radical. All right, so now what we've got is this methyl radical, and we've also created some HCl. Good for us. All right, so we're not done. We haven't formed a new product yet. All we've done is hit this methyl intermediate, and so we need to do a second step. And so in effect up here, we created 2 chloride radicals, and so we've got plenty of chlorine radicals sitting around. So what will happen, and really, the reaction between a couple of radicals, at least when they're there in a decent concentration, is pretty reliable and pretty fast. And so what happens is that our methyl radical, actually it's not going to be a methyl radical. Take that back. It's chlorine gas again. This is the first time I've taught this, so I'm still working through some kinks. All right, so basically what's going to happen is just like above where we had our chloride, which got split into radicals, that's going to happen again, except now it's going to happen between the methyl radical and one of the electrons on the sigma bond. So what that will produce is we've snapped one of our chlorides to our carbon, and so there's our product, right? We've been trying to form this all along. What else are we forming in this process? We are forming another chlorine radical, right? And so this is kind of like those additions of strong acids to alkenes, where at the end of the cycle, we regenerate the acid, right? So we only need a catalytic amount. It's the same thing here. So this happens a little bit. We have our initiation that just barely happens some, and we get some radicals. And then our chlorine radical comes down here, and it starts off this propagation step. And so at the end of the propagation step, what we've ended up with is our product, but also we've regenerated another chlorine radical. And so now this chlorine radical is free to go right back up here and kick off another propagation step. So lots and lots and lots of methyl radicals and lots of products can be generated from the result of really just one initiation step above. All right, so the initiation doesn't have to happen much. The propagation, where the action is, actually happens a lot. So this is going to be the main part of our radical chain mechanism, the propagation step. All right, so then finally, we're running out of starting material. We've still got some radicals in our pot. And what do you think the last one's called? That is the termination step. All right, so the termination step is ultimately going to destroy our radicals. And so again, we never have that many radicals in our reaction. Theirs are kept to a relatively low concentration. And so again, the termination step doesn't happen that much. And so I mean it. When the initiation step happens a little, we form some radicals, and once we've got a few, we're pretty good to go. And so then we hit the propagation step, and a lot of that is just going to churn out starting material over and over and over and over again. And then finally, when we run out of starting material, now our radicals are finally going to be able to react with each other. And so there are a lot of possibilities there. So what we can see is, say, some of the chlorine radicals come back together. So we can reform some chlorine gas. Or let's see, we could have a methyl radical react with some chlorine. And so in effect, what that will do is actually lead us right back to our product. So that's actually useful. But again, this isn't going to happen in any real appreciable amount. This isn't where our product comes from. Our product is coming from the propagation step above. We could also have something where, say, the methyl radicals happen to bump into each other. And so in effect, what we end up with there is going to be ethane. We weren't trying to get ethane, but we made a little bit of ethane. But again, if I asked you for the product of these reactions, are you going to list this? No, because this just happens a tiny amount. It's not an appreciable amount. It's just how our radicals end. Radicals are not infinitely stable, and so once they don't have any material to react with, they're just going to pretty much collide with each other, and they're going to turn back into something that's a lot more stable. So there's lots of possibilities for our termination step, but it doesn't happen much, and it really is just going to happen at the end of our reaction. All right. So there's lots of interesting thermodynamic information about this reaction that I'm honestly, we're going to skip past because, again, I want to get to some of the more interesting things. So the reason we're going to skip this is there's a lot more important stuff next week that we're going to talk about. So it's just something that we're going to cut out a little bit. But we'll still talk briefly about the thermodynamics. Because what we can see is regio and stereoselectivity. And so one question we might ask ourselves is, which halogens do this? So what we've seen thus far is going to be chlorine. And so in reality, let's see, we've got 4 possible halogens that we can consider. And so we see a trend. So on the left side, we're going to have our more reactive halogens, at least in the sense of this reaction. And then we're going to work our way down. And so what you can see is that if we're towards the top of the periodic table, we're very reactive, and as we work our way down, we are much less reactive. All right, so over here, we have our less reactive halogens, iodine and bromine. So let's think about what happens. So fluorine, which is the most reactive, it's so reactive that it's reactive to a fault. And so what we find is that the delta H for the reaction, for the radical reaction of fluorine, is something like minus 431 kilojoules per mole, which honestly is equivalent to adding a little fluorine to your flask and it just boiling over and exploding. And so it is so reactive, it is so exothermic that it's not really reasonable to actually run this reaction. Yeah, it reacts, but it's too reactive, and it's so reactive that it's not actually synthetically useful. And so it's not used. Yes, it's reactive, but no one uses it because no one's actually trying to just blow stuff up. All right, so on the other end of the spectrum, what we have is iodine. And so the reaction with iodine actually is actually no longer exothermic. It's actually endothermic. And so it requires 55 kilojoules per mole of energy to actually undergo this reaction. And so if we don't put extra heat into the reaction, will anything happen? No, and so in fact, if we put heat into some of these reactions, it pretty much screws all the reactions up, and so iodine is a no-go as well. And so this is very like Goldilocks here, where we have stuff that's too hot and stuff that's too cold, and then right in the middle, there's the 2 things that are perfectly fine. So it's going to be chlorine and bromine that we actually run this reaction with. And so just, let's see, the energy levels for chlorine, it's about minus 104 kilojoules per mole. For bromine, it's about minus 33 kilojoules per mole, and that's manageable. Much more manageable than minus 431 kilojoules per mole. That is stronger than a lot of bonds. All right, so let's talk about regioselectivity. And so what we can have is if we take a simple molecule like propane, so we're going to react it with bromine and some light. And so what we have is a possibility to form two products. And so we could form where the bromine adds to the secondary position, or we could add where the bromine adds to the primary position. And so knowing what we know about the stability of radicals, what do you think is going to be the major product, left or right? Which would be the more stable radical, the secondary radical or the primary radical? Definitely secondary. And so we see really good regioselectivity based on the strength of those bonds. So in reality, we'd see that this is about 97%, where the primary product will form about 3%. So we see really good regioselectivity when we use bromine. Unfortunately, when we do this reaction with chlorine, it is not quite as good. So if we take the same starting material and we consider forming the secondary product versus the primary product, the regioselectivity that we get is something on the order of 60% to 40%. And so ultimately, we're not going to get into the reasons why that is. It would take a good 10 or 15 minutes to really work through it, and I don't want to spend that much time. But basically, what I want you to just know is that when you do this reaction, you still see regioselectivity of the chlorine. It's just not very good. And in fact, what we can do is we can come up with a very general ratio of the products that we see. So if we have bromine and we have chlorine, and so we talk about the ratio between a tertiary, a secondary, and a primary, what we see is that ratio for bromine is very good. It's about 1600 to 80 to 1. Whereas with chlorine, it's something like 5 to 4 to 1. And so we're just going to say that this is due to thermodynamic reasons. All right, so selectivity is awesome with bromine, but it's just not the case with chlorine. So in addition to regioselectivity, we should consider the stereoselectivity of these reactions. And so when we started talking about radicals, when we considered stereoselectivity. All right, so when we started talking about radicals, we talked about the hybridization, or at least what their hybridization is kind of like. And so what did we say? All right, so of course, it's basically, we don't need a full fourth hybrid orbital, right? So it's kind of like sp 2.5 or so, but really it skews towards sp2-like. And so that's how we actually consider radicals. So we can say the radicals are sp2-like. And so that's important because sp2-like or sp2 hybridized atoms are planar. Can we have a stereocenter in an sp2 atom? Can we have a chiral center? No, we can't, right? We've got to have sp3 hybridized atoms. And so this is significant in terms of the stereoselectivity that we see. So there's two cases we want to think about. We can start with something like butane. And so in butane, what we'll have is we can take bromine and react it with light. And so the major product, is it going to add to the secondary carbon or the primary carbon? Secondary, right? Now consider that we're going to go through a radical that is like this and is sp2-like. What we have to do is we have to consider that this radical is going to be very planar, just like a carbocation. So what that means is that bromine, again, can attack from the front face or it can attack from the back face. And so ultimately what we're going to see in this case is two different products where the bromine is on a wedge and the product where the bromine is on a dash. All right, so the starting material of butane, is that optically active? Does that have a chiral center? No, and so the starting material is not optically active. What about the products over here? So if we take an individual of these products, is that individual product optically active? Sure, but that's not what we get. We actually get a racemic mixture here. And so are our products together optically active? No, they are not optically active, and we're going to see in a sec why I'm pointing that out. So what we could also do is we could start a reaction with an optically active starting material, so something with a chiral center. And so for example, we could start with this compound. And so when we look at this compound, when we go to react it with some light, is the starting material optically active? Does it have a chiral center? Yeah, so we have a chiral center. And so our starting material is optically active. And so let's think about what's going to happen. So what's going to be the most stable position? Is it going to be one of the primaries, or the secondary, or the tertiary? It's definitely going to be the tertiary, right? Because the tertiary is most reactive. And so what's going to happen is we're going to go through an intermediate that looks like this. And so it's sp2-like, which means we're going to flatten it out into a very planar sort of shape. And so we had we had stereochemical information here, right? But as we go to our intermediate, have we retained that stereochemistry? No, because now we've lost the sp3 hybridization. We've turned into an sp2-like hybridized orbital. And so what happens is, again, our bromine, it can attack from the front, or it can attack from the back. And so the unfortunate aspect of that is now, in our flask at the end of our reaction, all right, so we started with optically active starting material. Is our flask still optically active? It's not, right? Because again, what we've ended up with is a racemic mixture which is not optically active. And so typically it is not a good reaction if we're losing stereochemical information, because it can be tough to build into our molecule, right? We had one enantiomer here. Over here we actually have both enantiomers, and now we have to deal with the fact that we've lost that selectivity. So you can start with a chiral material and end up with a pair of enantiomers that together are not optically active, and now you've got two products. So that's a little bit of an unfortunate result. All right, so moving on. Bromonyl number 3. This will be a allylic halogenation. And so we have a material that looks like this. We're going to have really 3 different hydrogens here. We have this hydrogen, and this hydrogen. How many peaks would we expect, or how many signals would we expect in an NMR spectrum? We'd expect 3, right? Because we've got symmetry right down the middle, and so this one right here would be equivalent to one that was at that position. So we'd see 3 different proton signals. And so let's think about these CH bonds. Which do you think is going to be the weakest? Well, we want to think about what's going to form the most stable radical. Will the most stable radical be right there? Definitely not, because that's an sp2 hybridized radical. That's not very good. All right, so down here, we basically got 2 secondaries. Is there a difference between those 2 secondaries? Definitely, right? So this one's going to end up sitting next to a pi bond. And so what we've got is an allylic CH bond here, which means that's going to be the weakest. So it's going to be our allylic CH bond, which is weakest. And so what will end up happening is we're going to go through an intermediate. All right, so we have this radical. And so we can draw resonance structure for this radical, which explains why it is so stable. So we see, in effect, what we have are 2 radical-like positions on our product, right? Or at least on our intermediate. So we could expect reactivity right there, and we could also expect reactivity right there at that position. It's because both, through resonance, have radical-like character. All right, so let's actually write that down. Both positions have radical-like character. All right, so let's see if we can do this reaction. Let's take the same exact starting material, and let's react it with bromine. What's going to happen? Are we going to see any radicals form? Why not? Yeah, we don't have light, right? But even more importantly than that, because yeah, we haven't added light, but much faster than the radical reaction we might expect to occur. Have we seen a reaction between an alkene and Br2? Yeah, we absolutely have. And so that's going to be a much more favorable pathway. So if we don't add light, and in fact, even if we had added light, this would be the major product. What we're going to end up with is a type 2 electrophilic addition, where we end up with anti-additions of our bromines. So that means we're going to have this plus an enantiomer. And so we've done that before, and this really wasn't the goal in the first place. So we've got to come up with a more creative solution than just using bromine and light. All right, so we can't use Br2. So there are a lot of possibilities, and so the most commonly used is going to be referred to as NBS. And so NBS stands for N-bromosuccinimide. And so there's also N-chlorosuccinimide, which can do the same thing. So we've got both of those reagents. And so essentially, what we're going to do is we're going to be able to create radicals without having to worry about the electrophilic addition pathway. It basically rules out this reaction up here and allows us to go the pathway that is a little less favorable, but in this case, by using NBS, it's the only place to go, and so that's what actually happens. What NBS looks like, so it's going to be a 5-membered ring with nitrogen, and so we've got a couple of carbonyls, we've got a carbonyl there, and so it's N-bromo, so what do you think substituent's sitting on that nitrogen? Yeah, it's going to be a bromine, and so in effect, what we're able to do is by taking NBS, or N-bromosuccinimide, and then hitting that with some light, we're able to undergo homolytic cleavage of our NBr bond. And so one thing that we create, I guess, is this succinimide radical. But more importantly, it's a way that we've now generated bromine radicals without needing to use bromine Br2, which we know is actually going to prefer to undergo the electrophilic addition reaction. So we have to get a little bit creative to avoid undergoing a reaction that we've already learned about. All right, so in this case, mechanistically, we've already seen the initiation step. This is it. We use NBS to initiate our radicals, which leads us to the propagation step. And so in our propagation step, what we're going to have is, let's see. We'll use starting material that looks like this. All right, so what we have is, of course, this CH bond. And so this is going to be an incredibly weak CH bond because not only is it on a tertiary carbon next to a pi bond, so it's a tertiary allylic CH bond. And so what we can do is, now that we've initiated some radicals, we'll have our bromine. What's going to happen is our bromine radical is going to abstract the proton. And so again, we draw fishhooks. And so in effect, we're going to form this radical plus HBr. And that's going to be important in a second for reasons that we'll see. All right, so one of the reasons this is such a stable radical is the fact that we can draw a resonance structure for it. And so again, that resonance structure would look something along the lines of this. And so we have both a tertiary and a primary radical. Now, of these two resonance structures, which do you think contributes more, the one on the left or the one on the right? So it's a primary versus a tertiary, and so they both have the resonance stabilization, of course. So ultimately, we would maybe expect this one to be the more stable radical, but certainly because of resonance, this structure right here, this carbon right here, would also have some radical character, just like we would expect it to have some carbocation character, even if it's not the most. All right, so I said that it's important that we form some HBr, and for this mechanism it really is, and that's because the HBr that's generated is going to react with NBS to create some Br2. Not enough that we're going to undergo the electrophilic addition pathway, and you don't need to know mechanistically how this happens. You just need to know that some Br2 will be generated from the reaction of HBr and NBS. And so now that we've got bromine that's been generated, we've got two possibilities. So what we can see is reaction of this radical with our bromine. And so this would look like this, such that we will generate this tertiary product. Alternatively, what we could see is it react at the primary position. So in that case, what we've got would be the primary bromide right here. So two possible products are going to be possible because two products will be possible because we've got both a tertiary carbon that has radical character and a primary carbon that has radical character, and so we end up with two products. Which is going to be favored, do you think? What's the major product? And so likely the tertiary product is going to be the major product, because here we've got, well, let's not say more stable because it's a resonance structure, but we'll say that it's the major contributor. How's that? So we've got a major contributor here, which leads to this being the major product, and so we would end up with the primary bromide as the minor product. All right, so let's just let's see. Let's do an example of this, and so our example would say you could find yourself in a situation where you've got this starting material, and we're going to react it with NBS and light. And so what we've got to consider first is what's the weakest CH bond. And so we can pretty easily see that we've got an allylic CH bond there, which means we're going to have a reactive position there. And we're also going to have a reactive position there due to resonance. And so we're going to have multiple products. One of those products will be from the addition of a bromine to that position. And so in effect, through resonance, we'll move our double bond into the ring. And so we've also got the possibility that we're going to add our bromine to the secondary position here. And so of course, since we could form a new stereocenter, what we'll end up with is a bromine on a wedge as well as a bromine on a dash. And so what are the major products of this reaction? 1, 2, or 3? Probably 2 and 3, right? Because that's the result of a new reaction that's gone through a secondary intermediate. So this would be our major, and this would probably be our minor. I think it's fair on an exam for me to expect you, for allylic halogenation, to determine what possible products. So to draw all 3, I think, would be perfectly fair. All right, so finally, we're going to get to Roman numeral number 4. And so Roman numeral number 4 is the radical addition of HBr. And so in the radical addition of HBr, we can take a starting material, looks like this. And so have we done this before? Yeah, so this was back to a couple chapters ago when we did the electrophilic addition of a strong acid to an alkene. And so we know, is this going to be Markovnikov or anti-Markovnikov? Definitely going to be Markovnikov, right? Because we're going to protonate the primary carbon such that we have a tertiary, more stable carbocation. So in this case, we've got a Markovnikov product. And so that results from an electrophilic addition. What we find is that if we have HBr, but instead of reacting it with HBr alone, and instead we put some peroxides in there. And so what a peroxide is any molecule where we've got 2 oxygens bonded together. So here we've got a peroxide. Peroxides are those things, it's the reason we tell you not to distill in lab down to a dry pot. It's because we could have some peroxides in there, they're not very stable, they're potentially explosive, and so that reactivity is what we utilize here. And so they're very reactive and will generate radicals. And so in effect, why would I be doing this if we got the same product? We're going to get a similar product, but do you think it's going to be Markovnikov? It is not. So in fact, this is a way that we can actually obtain the anti-Markovnikov product. So now we've got another pathway that we can undergo this HBr addition. And so if we do it with peroxides in there, we can end up with the anti-Markovnikov product. So why do we end up with the anti-Markovnikov product? So first off, our initiation of our radicals is going to come from the reactivity of the peroxide. So essentially, we're going to hit our peroxides with some light. And so in effect, what we see is the generation of 2 oxygen radicals. And so from there, what can happen is in our propagation step, our oxygen radical will then react. And in fact, this is a continuation of the initiation step. So our oxygen radical can react with some HBr that we know we've already got in there. And so what will happen is it'll abstract that hydrogen as such. And so what we end up with is an alcohol plus a bromine radical. And once we've got that bromine radical, it's where we can go down the road and undergo our actual transformation. All right, so there's going to be two possibilities. So let's take a look at the, we'll use the starting material that I showed. If I remind myself of this. All right, so if we have these starting materials, so here's one case, and it's going to be the same starting material, but we're going to see what happens if we go with different regioselectivity. And so in effect, in both cases, what we'll react with is going to be a bromine radical. And it's going to react with the pi bond. So what we see is that part of the pi bond will go to form our new CBr bond, and then the other will generate a radical. So in this case, what we've got is we've generated this intermediate. If we go the other way and we attach the bromide to the tertiary position, what we end up seeing is this newly generated radical. And so when we look at these two new intermediates, which is definitely more stable? The left one or the right one? Definitely the left one, right? Because what we're looking at is a tertiary radical here versus a primary radical here. And so because we've got a tertiary radical, it's more stable. And since it's more stable, we end up with that anti-Markovnikov addition favored. All right, so that's why we end up seeing anti-Markovnikov addition. And so once we get to this point, what we have is our radical will react with another molecule of HBr like this. So we end up with our final product, which is the anti-Markovnikov addition, and then in effect we've regenerated our bromine radical, which can go back and do our chain all over again. Okay, that is it. That leaves us 3 minutes to do fun facts. Okay, really quickly. Roman numeral number 5, fun facts. Don't even know why I'm writing it out. All right, so fun facts with radicals. I've got two cases. So who's heard of CFCs before? All right, so you're right. That's chlorofluorocarbons, right? And so an example of chlorofluorocarbon would be something like dichloro-difluoromethane. And so why this matters is, I don't know, I like food. And so I have a refrigerator, and I probably also had a refrigerator, you know, one of the early models if I were born in 1930 and lived in like 1950. Because we didn't know about CFCs and their damage until about the 1950s or 60s where some smart people figured it out. And so my refrigerator is going to be constantly ejecting these CFCs. And so one of these CFCs, for example, could be dichloro-difluoromethane. And so that looks like that. And so who cares, right? It's the 1950s. What bad could have come up with? All right. So unfortunately, we've got Mr. Sun. Oh, Mr. Sun. I don't know why I didn't use yellow. There's yellow. All right. So what's happening is, in effect, Mr. Sun is beating down on this molecule. And what is it beating down with? Uh-oh. And so in effect, it's going to hit it with light such that this chlorine radical is going to jump off. Or we're going to at least undergo homolytic cleavage here. And what we see is that we have this organic radical, which isn't that big of a deal. But unfortunately, we also generate this radical right here. And so what is that going to react with, you think? Uh-oh, yeah. And so once we have ozone up there, what can happen is we can form some species such as this radical, plus we can make some oxygen, which I guess isn't the worst thing in the world. We'll see why it is kind of bad in a second. And so eventually what results is a hole in ozone layer. And so we no longer use these CFCs. Instead, we use hydrofluorocarbons. So we replace the chlorines with hydrogen. And so those are better. They don't cause a hole in the ozone layer. They just contribute to global warming. So chemicals, right? All right, so then B. B is oxygen. And oxygen is really interesting because oxygen, you can't live with it. And ultimately, you can't live without it. Why is that? So let's make a pros-cons list for oxygen. So pros. I would say one of them would be aerobic respiration. I don't know about you guys. I like it. I think it's good. I take advantage of it constantly. Cons. Over time, kills you. Seriously, it's really, really bad stuff. It's this really complex relationship we have with oxygen. The reason that oxygen is pretty dangerous, in addition to it being very good, is that we skipped over a bunch of the molecular orbital stuff earlier in class because it's complicated, but the best picture that we can really think of as oxygen is this one right here, where we don't have a double bond, and in fact what we have is a diradical. And so we have to use this oxygen in our bodies, right, for aerobic respiration, but in effect we have potential radical reactions that can result from this oxygen. And that's exactly what happens in your body. So your body will sometimes accrue things like O2 minus radical or hydroxide radical. And so this stuff's pretty bad. This has been implicated in, it can go react with your DNA and mess that up. It can oxidize fatty acids, amino acids. Fatty acids and amino acids. By oxidizing amino acids, it deactivates enzymes. It's really, really bad stuff. It's implicated in cancer, heart disease. I think the current theory right now is that mainly oxygen is the reason we age. It's because it's just constantly doing damage to our bodies. And so our body has ways to combat this, right? So what do you take sometimes to help beat cancer or stave off cancer? Antioxidants, right? And so that's what antioxidants are doing. Now your body produces antioxidants to basically protect yourself because it knows that you're having all these radicals formed inside of you, but ultimately and always the radicals end up winning. But by taking vitamin C and vitamin E, which is used to make other antioxidants by your body, you can make yourself a little more impenetrable to those radicals. All right, I'll be out of town this weekend. I'll see you Monday.
Doctor, are you in your office today?
I'm skipping town as soon as possible.
Okay.
So,
All right. See you.
See ya.